Good morning, students. We'll start with the today's lecture. Okay, in the previous lecture, we have seen this. These are the topics we have covered. That is numerical based on the force on a differential current element and the force between differential current elements and the numericals based on it, right? And this chapter is completed. That is magnetic forces. Unit 4, chapter 8 is over. Next, we'll take up the last unit, and today I'm going to cover this chapter, right? Okay, time varying fields and Maxwell's equations, right? In the first initial few chapters, 5 to 6 chapters, we have studied only the static electric fields, static electric fields. With respect to that, we have seen several laws, the derivation, right, charge distribution, all those things we have studied, right? Then in one of the chapter, in the previous chapter, we have studied the steady magnetic field, right? But actually, in the practical real-time world, so whatever we have studied, those are concepts, right, with respect to static electric field and magnetic field, right? But in the real-time world, we have the time-varying electromagnetic fields. So there are well-developed Maxwell's equations in order to define the wave equation, right? So in this chapter, we are going to see what are the topics that are going to be covered in this unit is, that is introduction. We'll see the brief introduction, the Faraday's law, and the derivation. Okay, before seeing the derivation, we'll see the Maxwell's equations for static electromagnetic fields. Already we have seen this, but I have listed once again here. Then we'll compare with the Maxwell's equations for time varying magnetic fields, time varying fields, right? What is the difference between the Maxwell's equations between static electromagnetic fields and time varying fields? We'll see, right? Then we'll try to derive one or two equations of the Maxwell's derivation of Maxwell's equations. Only two equations will derive, and not all the equations, right? Because few equations already we have come across, right? Okay, coming to the brief introduction part, the Michael Faraday has conducted certain experiments, and he has found that the time change means time varying magnetic field will produce the electric field. It means changing magnetic field with respect to time will produce the electric field. This is what the Michael Faraday has found out by his experiment. Then, after some time, the Clerk Maxwell, James Clerk Maxwell, but he has not conducted any experiments, but theoretically he has told that the magnetic field means the changing electric field will produce the magnetic field, the reverse way, right? So, in the real time world, there is only existence of electric field is not possible because mutually they exist together. The electric field and magnetic field, they are mutually perpendicular to each other, right? So the time varying electric field will generate the magnetic field, and the time varying magnetic field will generate the electric field. But we'll concentrate on the my Faraday's law, right? Means the time varying or changing magnetic field will produce the electric field. That we will see, right? Okay, already you are familiar with the Faraday's law. Just a simple circuit I have taken, and this is the iron toroid, right? So iron toroid ring, iron toroid. We call it as toroid, right? So it is a magnetic core made up of iron. Okay, on one part of the side we have wounded the coil here, and one this is the on one part of the circuit the battery is connected, and on the other part of the circuit the galvanometer or ammeter is connected. Galvanometer, it will indicate the deflection of the current, existence of current, but ammeter will measure the actual value of the current, right? So, right, so one part of the circuit the battery is connected, on another part of the circuit the ammeter, which is used to measure the current, is connected, right? Okay, here there is a switch here, and this is the magnetic core. We call this as iron toroid. Already I told you, right? Okay, then whenever the switch is closed, what will happen? The current will flow through this wire, and the flowing current means continuously the current will be flowing, and continuously there exists a magnetic field surrounding it. So that will induce the EMF in this another part of the circuit. EMF is nothing but, we can treat that EMF as nothing but the voltage. That induced EMF is responsible for the current in the other part of the circuit, this part of the circuit. So whenever the switch is closed, it induces the EMF on the other part of the circuit, and there is a deflection of the ammeter, indicating that yes, there is a current flow in the other part of the circuit. Then what will happen? Yes, whenever the switch is opened, means what will happen? The reverse current means whatever the reverse current is there, the current will be reversed. Means here, once again, due to the current that is existing in the other part of the circuit, it is also responsible for generating the magnetic field here. That magnetic field will oppose the source. This we know it is termed as a Lenz's law, right? Because it is opposing the source itself, and the law that is given by Lenz, we call it as, rightly called as Lenz's law. Simply we'll try to understand, yes, the switch is closed, the EMF is induced, and current is produced in the other part of the circuit. And whenever the switch is open, the current that is produced in the other part of the circuit is responsible for generation of the magnetic field in turn, and that will oppose the original field, right? Okay, the variation of flux, the rate of change of flux is nothing but the induced EMF is equal to the rate of change of flux, that minus sign. We will see the Faraday's law next, okay, and the observations of the Faraday's experiment we'll see here in the next slide. Okay, already we have seen this, means the changing magnetic field will produce the electric field, or else we can say the time varying magnetic field will generate the electric field, right? Okay, the observations we'll see by the Faraday, right? A steady or static magnetic field cannot produce any current flow, right? Yes, the steady or static magnetic field cannot produce any current flow, but a time varying magnetic field produces an EMF, electromotive force, that may establish a current in the other part of the circuit, that is closed circuit. And this EMF is nothing but a voltage which is induced from the changing magnetic fields, right? That is one way, right? So the EMF is induced by the changing magnetic fields, or if the conductor is made to move in the magnetic field, then motion of conductors in the magnetic field will also result in the induction of EMF, right? But here in this case, the EMF is induced because of changing magnetic field, right? Okay. Then the induced EMF, yes, we will now give the Faraday's law, the mathematical form of the Faraday's law. The induced EMF is nothing but the voltage we told, so we will write it as E, right? Induced EMF E is equal to minus then d phi by dt. Just the statement is here. The induced EMF is equal to the time rate of change of magnetic flux linked with the closed circuit, the rate of change of flux. And this N indicates the number of turns of coils, either it may be at the primary side or secondary side. Just like we can treat this as transformer, right? Primary coil and secondary coil we say, right? Okay, so the induced EMF we call it as transformer EMF also, right? We'll see it later, transformer EMF, right? Okay, this is the mathematical form. Faraday's law can be stated as the induced EMF is equal to the time rate of change of magnetic flux linked to the closed circuit, right? Then N is the number of turns in the circuit and E is the induced EMF. Suppose let us assume that N is equal to 1, only one turn is there, then E is equal to minus d phi by dt volts, right? And this minus sign, it indicates that the current that is generated in the other part of the circuit, right, it will oppose the original field, hence that minus sign is coming. So this is given by Lenz's law, right? Okay, the same thing has been written here. The minus sign in equation 1 and 2 indicates that the direction of the induced EMF is such that to produce a current in the other part of the circuit, which will in turn produce a magnetic field which will oppose the original field. This is because this is rightly termed by the Lenz's law, right? Okay, already we have seen the Maxwell's equations for static electromagnetic fields. This we have seen in the previous chapter itself, right? Just I have listed because in the next slide, the Maxwell's equations for time varying fields. What is the difference between the set of equations in integral form as well as point form, also called as differential form, we will see, right? First one is Gauss law, right? So integral form and differential form, also called as point form, we will see. Closed surface integral of d dot ds equal to q, that is equal to volume integral of rho v into dv. This we know. Then point form is del dot d equal to rho v. This we see. This we know, right? Then the conservation of electric field. This also we know, right? The principle of conservation of electric field, right? Closed line integral of E dot dl equal to 0, and in point form del cross E equal to 0. The curl of E is 0. For static, once again I am underlining static. Whatever we are studying, these equations are with respect to static electromagnetic fields. Del cross E equal to 0. Then we have seen the Ampere Circuit Law. Closed line integral of H dot dl equal to I, and by definition of the current density, current passing through unit surface area, but I is equal to surface integral of J dot ds I can write, right? And point form is del cross H equal to J. This is point form of Ampere Circuit Law. Then yes, no isolated magnetic charges can exist, means either only I cannot take up only the north pole or south pole separated, both exist at the same time. So no isolated magnetic charges can be found. Also this law we call it as conservation of magnetic flux. Means the closed surface integral of B dot ds equal to 0. If I consider any closed surface, the amount of magnetic flux lines entering is equal to the total amount of magnetic flux lines leaving the closed surface. So closed surface integral of B dot ds equal to 0. This is integral form. And differential or form or point form del dot b equal to 0. If I apply the divergence for this, we will get del dot b equal to 0, right? So derivation we have not seen for any of the few equations we have seen. So only we will be seeing a derivation for time varying fields, not with respect to static electromagnetic. Already We have come across all these equations, most of the equations. Then we'll compare these equations with the time varying Maxwell's equations for time varying fields. Yes, just I have put this mark here. Means these two laws remain the same. Gauss law and no isolated magnetic charges or conservation of, they remain the same. This and this will not discuss once again. So here the conservation of electric field. Here we call it as Faraday's law. You can observe here closed line integral of E dot dl equal to 0. Here you can observe the closed line integral of E dot dl is equal to minus the surface integral of the rate of change of magnetic field over the given surface. Means here we will concentrate on the time varying nature of the fields. Means the rate of change of magnetic field will produce the electric field, right? So hence this equation is justifiable, right? The rate of change of magnetic field over a particular surface will give me the electric field, means, right? So the rate of change of magnetic field will generate the electric field. So del cross E is equal to minus dou B by dou T. This we will try to prove it later, right? So we will prove that del cross E is equal to minus, this is there. Then next, we know the Ampere Circuit Law here, closed line integral of H dot dl equal to I, simply I, right? Here, closed line integral of H dot dl equal to I. But there should be something with respect to time varying fields. What is that? I will tell you here. The rate of change of electric field here, D equal to epsilon naught E, that is one in turn the electric, we are analyzing in terms of electric field only. The rate of change of electric field will generate the magnetic field. You can observe here, the rate of change of electric field will generate the magnetic field. So this is the differential form, del cross H equal to J plus dou D by dou T. Here del cross H equal to J. But for time varying fields, the variation of electric field should be shown here, dou D by dou T. So it is also same thing here, right? Only these two laws will vary, Faraday's law and Ampere Circuit Law here, right, for the time varying. And we'll see the derivation for this, but actually we'll not call this as a derivation, but justification we can give for this. We'll see this, only these two equations, right? Others we are familiar. We will not see the derivation of these two equations, right? We'll see the derivation of point form of del cross, point form of Faraday's law and point form of Ampere Circuit Law with respect to time varying fields. We'll see this, right? Okay, we will see the derivation. Yes, show that the curl of E is equal to minus dou B by dou T starting from Faraday's law. This is with respect to time varying fields we are speaking, right? Okay. From Faraday's law, starting from Faraday's law, we know the Faraday's law statement, right? The induced EMF is equal to the rate of change of flux, the time rate of change of flux, d phi by dt, and this is the minus sign. This we know. Then the induced EMF is nothing but the voltage. It indicates the voltage in the closed path of the circuit, right? So it is closed line integral of E dot dl, right? So it is nothing but here, E is equal to what? So volt per meter. Then what is dl? It is meter. So meter will get cancelled. So we can write this equation, right? We can justify this, right? So the voltage in the closed path E is equal to, induced EMF is nothing but the voltage. E is equal to closed line integral of E dot dl. E is nothing but the volt per meter. You just will check the dimensional check, just whether this is right or wrong. Dimensional check, volt per meter into meter, right? We are getting volts, right? This equation. These are the Faraday's law. Then we will define we know the flux is given by the magnetic flux passing through the specified area is given by, we know this definition, surface integral of B dot ds. Call this as equation 3. Then yes, we will substitute this equation 3 in equation, means we will substitute this value of phi in equation 1 here. So we can, equation 1 is rewritten by substituting equation 3 there. E is equal to minus d by dt, d phi by dt. What is phi? Phi is equal to surface integral of B dot ds. Call this as equation 4, right? Okay, next we can equate equation 2 and 4 because they are same, right? So E is equal to closed line integral of E dot dl is equal to this. So E is equal to closed line integral of E dot dl, that is equal to minus d by dt of surface integral of B dot ds. We can equate equation 2 and equation 4, right? Okay, next we'll try to analyze. Here there are two conditions for the induced EMF, because next, in order to proceed with the derivation, we have to understand what are those two conditions for the induced EMF. We'll see one by one, right? So the first one is important for us with respect to this derivation. Second one also we'll see, just in order to gain the knowledge. That's all, right? Okay. The closed circuit in which EMF is induced is stationary here, right? The conductor is not moving, it is stationary, but that stationary circuit will generate the time varying magnetic field, means magnetic flux is varying with time here, right? So the current that is flowing through the primary of the coil will generate the changing magnetic field continuously, right? The magnetic field. But the coil that is wounded on the primary section, it is fixed, right? So it is not having any, the conductor is not having any moment. So it is similar to your transformer action. Hence we call this kind of EMF in these kind of circuits as transformer EMF, right? Okay, they will come to the second. Okay, let me discuss this, but we will make use of the first condition in order to in the derivation, right? Secondly, what will happen? The conductor will move in the stationary magnetic field, right? The magnetic field is fixed. Let us consider the permanent magnet, right? And the conductor will revolve, right? So here, if conductor is revolved, right, we can see that this will come. This is the generator action, and this EMF we call it as generator EMF. The same thing has been written here. The magnetic field is stationary, constant. It is not varying with the time, while the closed circuit is revolved to get the relative motion between them. Right here, the conductor itself is moved here. Okay, we will not see this here. We will see concentrate on the transformer EMF. Okay, we were here. E is equal to closed line integral of E dot dl minus d by dt of surface integral of B dot ds. But magnetic field is varying with time, right? So instead of d by dt, I can take this d by dt as partial derivative dou B by dou t, right? Because the magnetic field is varying with time. So dou B by dou t, the same thing using the first condition. So we can write this, right? So into ds. I hope you are getting this, right? Minus the same thing is written here. Closed line integral of E dot d equal to minus surface integral of dou B by dou t into ds. Is it fine? Call this as equation 6. Why we are writing this equation? Because magnetic flux is varying with time. You can see the transformer EMF here in this. Let us use the Stokes theorem. This is line integral. And Stokes theorem is nothing but line integral is related to surface integral, right? LHS. You can observe here closed line integral of E dot dl is equal to, using Stokes theorem, I can write this as surface integral of del cross E into ds from here to here, right? Using Stokes theorem, line integral is related to surface integral, right? This RHS is kept as it is. Okay. Next, we will assume that both the surface integrals are taken over the identical surfaces are similar surfaces, right? So we can remove this integration part. So del cross E into ds is equal to minus dou B by dou t into ds, right? Because we are taking the integrals over the same surfaces, identical surfaces. So del cross E into ds is equal to minus dou B by dou t into ds. Then ds will get cancelled. Finally, the curl of E del cross E is equal to minus dou B by dou t. So the meaning of this equation is, this is true only for time varying fields, but not for static fields. For static fields, del cross E is equal to 0 because there is no change in magnetic field. Here you can observe here RHS of the equation, the changing magnetic field, the rate of change of magnetic field will produce the electric field. The rate of change of magnetic field is producing the electric field, right? The same thing has been written. The time changing magnetic field, the time varying magnetic field will produce an electric field. So we have proved this equation. Del cross E is equal to minus dou B by dou t, right? Then one more equation we will try to justify, not the proof, but we can say it as a justification. So this is the last derivation of in this chapter. Show that del cross H is equal to J plus dou D by dou t starting from point form of Ampere Circuit Law, del cross H equal to J for time varying fields, right? Okay. You can observe this equation here. The change of electric field will produce the magnetic field, right? The rate of change of the electric field will produce the magnetic field. Okay, this we will see. So from point form of Ampere Circuit Law, starting from this is the point form of Ampere Circuit Law, del cross H is equal to J. This is this holds good for static electromagnetic fields. Static electromagnetic fields. But it does not hold good for time varying fields. So del cross H equal to J. You can observe for time varying fields, del cross H is equal to J plus the rate of change of electric field. So this should come into picture. So we will justify how it will come into picture, right? We will see. So this is not sufficient or inadequate for time varying conditions, this equation, right? So we will take divergence on both the sides. Why we are taking divergence means we will try to study the spreading nature. Means let us check, right? So means that I want to include the variation of the electric field that is generating the magnetic field, that we want to include. We will try to justify our answer, but not the derivation I am telling. Please concentrate. So take divergence on both the sides, right? So del dot of, right, and we are taking the divergence del dot of this quantity del cross h is equal to del dot of j, but we are equating it to 0. Why? Because the divergence of curl is 0, means this is the curl, right? Del cross h is the curl, so the divergence of curl is always 0. Please keep in the mind, we will make use of this. The divergence of curl is identically 0, right? So if this is equal to 0 means if I apply the divergence on RHS del dot j, it also should be equal to 0 as per this mathematical equation, right? So del dot j is also 0 because the divergence of curl is identically 0. Then next, what is del dot of j? From continuity equation of current, we know that del dot of j is equal to minus dou rho v by dou t. This is the point form of continuity equation, right? Continuity equation of current. This also we have studied there in the previous chapters. Del dot j is equal to minus dou rho v by dou t, right? But del dot j is 0 here, and we know from continuity equation of current del dot j is equal to minus dou rho v by dou t, right? But as per this, dou rho v by dou t should be made 0 so that this equation holds good, del cross h equal to j only, right? So but dou rho v by dou t cannot be 0 because we define the rate of flow of charges, means there is the rate of, if I consider any closed surface, the rate of flow of charges constitutes current, that is current density j, right? This minus sign is indicating there is a depletion of charges because continuously the charges are moving, but they cannot be 0 in this, right? So dou rho v by dou t cannot be 0. This is unrealistic limitation that we are putting, right? So this fails, this analysis fails. We will think of some other thing, right? We have taken divergence on both the sides. The divergence of curl is 0, but del dot j cannot be 0 because dou rho v by dou t cannot be 0. So we'll think of some other alternative. So we'll take the equation 1, we'll write it here, del cross h is equal to j plus g something. You will define some more vector. This g is actually dou d by dt, the rate of change of electric field. This we have to prove. This g vector is the rate of change of electric field. We have to get g is equal to dou d, that we will see it, right? So we will assume that we will add one more term here, del cross h is equal to j plus g for the time varying fields. TVF I am calling, not for static fields, right? Then we will apply divergence on both the sides now. Initially, without adding this term, we have seen the divergence that has failed. We cannot realize this. So we will add one more term here. We'll see what is this term, we'll find out this term and we'll justify our answer. Take divergence on both the sides. Once again, we know that this is the curl, the divergence of curl is 0, so this will become 0. The divergence of curl will become 0. Then apply the divergence to this and this, del dot of j plus del dot of g, del dot of j plus del dot of g, right? I hope you are getting this, right? Okay. Then I will rewrite this equation here, 0 is equal to del dot of j plus del dot of g. Okay, fine. Then what is this del dot of g? Thus del dot of g is equal to dou rho v by dou t, because why I'll tell you why del dot of g is equal to minus dou rho v by dou t, because we know that del dot of j is equal to minus dou rho v by dou t. This is from continuity equation of current, right? So del dot of j, we know that del dot of j is equal to minus dou rho v by dou t. This is point form of continuity equation. So del dot of j plus del dot of g should be 0. If del dot of g is dou rho v by dou t, means dou rho v by dou t minus dou rho v by dou t. So it will become 0. So we can justify that del dot of g is equal to dou rho v by dou t. Is it fine? Because del dot of j is equal to minus dou rho v. So I have to add this so that this will become 0, right? Okay, now we came to know that del dot of g is equal to dou rho v by dou t. Then replace this rho v by this del dot d equal to rho v. We know that, right? Point form of Gauss law, del dot of d equal to rho v, right? So instead of rho v, you can write del dot d. So del dot of g is equal to dou rho v by dou t. What is rho v? Rho v is equal to del dot of d, right? Yes, by the vector identity, just we can shift it. We can take this partial derivative inside and del outside. So we can rearrange it, no problem. Mathematically, it will not affect, right? So del is taken outside and partial derivative with respect to d. So del dot of dou d by dou t, I can write it. Mathematically, they are one and the same, right? That doesn't make any difference. Okay, this we have seen. Just observe this and this, del dot of g, del dot of g. But then what is g? G is equal to dou d by dou t. So g is equal to dou d by dou t. We came to know that g is equal to dou d by dou t. So substitute in equation 2. G is equal to dou d by dou t. So substituting in equation 2, del cross H is equal to J plus G is nothing but dou D by dou T. This is holds good only for time varying fields. But for static fields, there is no variation. This will be 0. So del cross H is equal to J for static fields, static electromagnetic fields. So looking at the equation, we will come to know that the rate of change of electric field will produce the magnetic field. The rate of change of electric field produces the magnetic field. The same thing as the rate of change of electric field produces a magnetic field. Right? Okay, this completes the last chapter and also the syllabus. Happy ending and thank you. Right? Okay.